name is Sridhar Ramanathan. Hello, can you hear me?
Yes, sir. Please continue.
Yeah. So good afternoon, ladies and gentlemen. My name is Sridhar Ramanathan, and I'm going to present to you the paper on predicting fuel uplift for an aviation fueling company. The slide here shows you how I'm going to proceed with the presentation. Uh, this presentation is part of our curriculum for great learning, and my teammates here are Asmita, Revati, and Sudarshan. And basically, fueling an aircraft is also known as into-plane fueling services. There are two basic types of into-plane fueling services. One is hydrant type, and the other is Bowser operated. In hydrant type, we have underground pipelines which are laid to supply fuel to the aircraft, which are safe and also can provide you with an unlimited supply. In Bowser operations, the fuel which is supplied is with the help of tankers. So the tanker size, the fuel supplied depends on the tanker size. There's 16 ton, 26 ton, and 45 ton Bowsers. So the major drawback in this operation is that once the Bowser has gone and refueled an aircraft, there is a lot of time which is wasted because the Bowser has to come back and top up its Bowser again so that it can carry forward the next operation. Now the problem the company faces right now is that we receive the final fuel only at the time which is closer to the departure of the aircraft. This makes it extremely challenging for the aviation company to manage its inventory and also to increase the efficiency of its manpower. Now, our paper here proposes that uh, our, uh, our paper here proposes to predict the fuel volume which will be uplifted by these aircraft, which are scheduled in nature, and we use a linear regression model to solve this. Now, let me explain to you about the related work in this domain. Now, existing work has already been carried out in the terms that the fuel consumption with respect to the airline, and the airline uses information such as fuel on board, reservation data, flying altitude, aircraft sensors data which are available. These data are not available to an aviation fuel company. With the minimum known variables, we are trying to predict how much volume will be uplifted by the aircraft. These two are reference papers which used aircraft fuel consumption as a pattern. Now let me explain to you about the data. The data here, which was collected from the company's custom software, it generally enters data from each fuel engineer after completion of one operation. So the data here consists of sorry. So the data here is for a period of 1 year from April 2018 till March 2019 and uses around 63,000 records from a hydrant dispenser type of an operation. The operation is based out of Mumbai and we use 37 variables for each operation. Now this here is the sample of the data which have been used for our analysis. These are the major predictor variables. Now let me explain to you about the linear regression model. So here, since the aviation fuel company uses only minimum data available to them, we choose destination and aircraft body type as our main variables for our analysis. We confirm this using an ANOVA. There were other variables like flight ID or airline, which could also be used, but it resulted in an overfitting of the model. I know this is the equation for our volume prediction. Here, y hat represents the volume which will be predicted. Beta naught is the coefficient of intercept. Beta 1 d and beta n d are the coefficient of different levels of destination, and beta 1 b and beta 2 b are the coefficients for different level of body type. Now let me explain to you the interpretation of this equation. Our model here was used to predict volume uplift for 112 destinations using different aircraft types like ATR, we consigned all narrow body aircrafts into one category and all wide body aircrafts into one category. So we used three different types of body type: ATR, narrow, and wide. Now let us just explain to you this in a little more detail. Now a flight which is operating from Bombay to Delhi and uses an aircraft type like ATR would generally take around 2,865 liters, which has been mentioned here. We use Delhi to Bombay as a baseline for our analysis. The destination, the coefficient for Goa is seen here as minus 1697. This indicates that the distance from Mumbai to Goa is comparatively less than the distance from Mumbai to Delhi. You can also see that the coefficient for JFK, which is in USA, is around 1,41,835. This signifies that the distance from Bombay to New York is quite large. We also here found out the intercept for narrow body aircraft as well as wide body. The narrow body takes around 2,159 liters, and for wide body it is around 13,799. Now the overall interpretation. When we use the ANOVA table, we found out that the F static value for all the variables showed a high level of significance. Since the F value was less than 0.05, we considered most of the variables playing a significant role. We found out that the multiple R square and adjusted R square is equal to 94%. This means that almost 94% of the data was 94% of the data was validated using with respect to volume. The model satisfies the assumption of linearity and homoscedasticity was satisfied, though the residual distribution was was not perfectly normal. In this graph, this graph shows us the value of volume with respect to actual and predicted. There is a clear positive track between actual and the predicted value. In the backtracking plot, that is the second graph, you can observe that it is observed that the predicted volume is almost follows the actual line. I can conclude by saying that the regression model here provides us proof that we can use a data-driven approach to predict volume for fuel uplift, which can be used by the oil companies instead of the general heuristic measures which are employed. The prediction of volume can be used as a starting point for optimizing shift operations. The applications for this can be used to calculate fuel time based on the predicted fuel volume. We can also plan the amount of manpower required per shift and also to schedule preparation. Then we can also optimize the movement of tanker, which also will help in reducing operational inefficiency, and also that we can also maintain periodic maintenance and also periodic checks. And we can also understand the overall volume which will be required for a horizon of 3 to 6 months. Now let me take you to the step where what can be our future goals. The work can be extended into many aspects. Basically, since the model is generic in nature and not specific to the case study company, we can apply this across different oil companies across the globe and to different airports. The existing study is based on one departure airport. So the care must be taken that while applying this model to a different airport, you should study about the flight pattern for it to be applied in a systematic manner. Then we can also use one model for every airport and also a single point of reference for each arrival and destination airport. I would like to thank you. I would like to conclude by saying that the volume which has been predicted can be used as a model for all future aviation oil companies so as to increase efficiency and implement an automation approach in their work. That's it, sir. Thank you.